Hey guys, welcome to example 1 of 9.2 binomial expansion. Now we had just done the warm-up and I threw in those a and b terms. The reason why we did that is because for binomial theorem we're basically trying to be able to do a plus b raised to some power, but maybe it's a plus b to the 32nd, right? This is going to get awfully large. A plus b to the 5th has 6 terms. A plus b to the 4th has 5 terms. A plus b to the 3rd has 4 terms, right? So a plus b to the 30 something is going to have 30 something terms. The work goes up exponentially, so we're not going to want to do that. So binomial theorem is basically an algorithmic way to do binomial expansion without having to shoot yourself in the head, because it's just tedious and basically impossible if you want to go to really high numbers without doing it in a brute force fashion. So the very first thing we want to talk about is that n represents your exponent in these cases, and the number of terms is always n plus 1. So if I have 35 as my exponent, then there would be 36 terms in the full expansion. You did this last year using Pascal's triangle, or you might have done it last year with Algebra 2. But if you didn't, Pascal's triangle is basically starting with these ones on top, flanking ones on the side, and you'd have to find 1 plus 1 is 2 to get this 2. To get this 3, you'd say 1 plus 2 and 2 plus 1. To get this 4, it's 1 plus 3. To get this 6 is 3 plus 3. To get this 10, it's 6 plus 4, and so forth. And you can keep going and expand this triangle out. So the coefficients, it turns out, instead of having to draw this triangle out, where each one of these numbers is the sum of the previous two terms, it's a Fibonacci sequence, we can use combinatorics from chapter 9.2. It turns out that you can get these numbers, these coefficients, just by using combinations, where n is the exponent and r has to do with which term you're looking for. All right, and we'll talk about that in example 1 here. The second part of the pattern for binomial theorem has to do with the exponent, and that's why I threw in those a's and b's to the 0, because as you can see, a to the 5th, you're going to start with an exponent of 5 for a and an exponent of 0 for b, but a is going to keep descending, so a to the 5th to a to the 4th, a to the 4th to a to the 3rd, then to the 2nd, then to the 1st, then 0. And then b starts at 0 for its exponent, but goes 1, 2, 3, 4, 5. And recognizing those two patterns with the exponents and with the combinatorics for the coefficients basically allows you to expand anything without having to go crazy drawing giant Pascal triangles. All right, so let's try example 1. The first thing we want to identify is the n. In this case, it's 5 because the exponent is 5, which means that there are 6 terms. Oh, and another thing I want to note is that the notation for combinations can be written 2 different ways, and I've seen both of them enough that you should just really know both. And it's rather simple. So as an example, 5C3 could be written as 5,3 in parentheses, just like that. They're the same thing, all right? So no confusion there, and I'll just write it with parentheses just so you guys get used to it, because you've already seen the combinations notation with the capital C. So how do we start this? The first thing we could do is just write our coefficients in terms of combinatorics. Because our n is 5, then we're going to start with 5C0, right? And we're going to want to keep doing this until we get to 5C5, because after you get 5C5, 5C6, you're just going to get 0. So 5C0 all the way up to 5C5, leave some space in between. So 5C0, 5C1, or 5 choose 2, 5 choose 3, 5 choose 4, And 5, choose 5. You know you're going to have A and B as your as your variables. So I'll just write A, B, A, B, A, B for each of them. But again, we understand that pattern. The A starts with the 5th power and then goes down and descends, while B starts with 0 and ascends. And then just add everything in between. All right, 5C0 if you want, or, you should know that. Well, after this, you'll realize 5C0 is 1. You throw that in your calculator just to review. You'd hit the number 5. You go to math, go to the right to probability, and then it's choice number 3. And you put a 0 there, you hit enter. And then you can also press second enter to get it again, and then just go back and change that to whatever you want, right? And you'll realize the combination 5C0, 5 choose 2 is going to be 1, A to the 5th, B plus, and again, that was then 5, A to the 4th. Oh, actually, sorry, that B should not be there, right? Because B to the 0. And then this be B plus 10, A to the 3rd, B squared. Now remember, we have 3 terms for a 6-term expansion. Pascal's triangle is symmetrical from the center, right? Its left side and right side are symmetrical, which means that once I get to the middle of Pascal's triangle, if I don't know it and I don't want to calculate it by hand or with a calculator, I don't have to, because the other side is symmetrical. So then on this side, it would just mirror, the left side in terms of the coefficient. It'd be 5, AB to the 4th, and then plus 1, B to the 5th. And that would be your full expansion. I'll see you guys in example 2.